Thank you.
Thank you. My name is Emmanuel Mavhura. I'm based at Bindura University in Zimbabwe. Together with my colleague, Tawanda Manyangadze, we've been working on strengthening drought monitoring in Zimbabwe using a technical convergence approach. Why the drought issue? In Africa, sub-Saharan Africa, especially in the southern part, drought is one of the major disasters that we are faced with. Currently, it is threatening millions of Zimbabweans. About 9.4 million people are food insecure. This is slightly above half the population of the country. But again, in the past 30 years or so, there have been notable droughts, like the 1991-92 drought, the 2015-2016 drought, 2018-2019, just to mention a few. Now, the vulnerability of the population in Southern Africa is high, probably partly due to high dependence on rain-fed farming system. But the impact goes beyond the agricultural sectors. We've got non-agricultural sectors that include fisheries, hydroelectric power generations, and many more that are actually affected by the drought. So this is a major drought disaster that we are actually faced with. In view of this, the key research question is, in what ways can the drought risk be scientifically monitored and analyzed to show the geographic extent, severity, and duration of the drought hazard across Zimbabwe? To answer this question, we thought of a composite drought index, which is basically a drought monitoring and analysis tool. The tool uses either observed data from the meteorological offices or remote sensing data. The interesting part is that it uses 4 parameters that reflect components of the agricultural drought. Which are these 4 parameters? 1, it is standardized precipitation index. 2, evapotranspiration. 3, it is normalized difference vegetation index. Simply put, this is about the vegetation health. And the 4th one is soil moisture. Colleagues from who are actually familiar with the climate change research field understand very well that you can do well to monitor drought using either SPI alone, standardized precipitation index, or you can actually focus on evapotranspiration alone, including the others. But in this case, our approach uses a convergence of evidence approach. The CDI as a tool can be developed on monthly basis or even on seasonal basis. But one thing that is interesting is that the parameters that we have talked about should be weighted. And there are various ways in which you can actually weight and then validate the CDI. So the idea of the convergence of evidence approach is coming into fact that using the weights assigned to the 4 parameters, you then blend the 2, the 4 rather, into one composite index, which is the composite drought index, CDI. So our journey in developing the CDI took 5 processes, 5 stages. As you can see, the first stage is about collecting climate data. This is from satellites, surface observations. You can also use some computer modules. The second one is about selecting the drought indicators, which are context-specific to your area. These are based on data availability, of course, the quality of the data, the decision-making needs that are in that place. Having done that, the third stage is about putting the data in historical context. You can either use the percentile method, which is used to rank the data and assign the severity of each and every data. Then the fourth stage is about assigning weights. In our case, we thought standardized precipitation index contributes largely to the CDI, and therefore we gave it 40%. The other three parameters, we gave them 20% each. So having assigned the weights, the fifth stage is about blending the data to create the map into a single product with the relevant information for the drought. So you can actually see at the bottom of my slide here that we've got a map showing the Zimbabwean map showing the NDVI, another map, evapotranspiration around, the other one, precipitation, soil moisture. Then the last map is a composite drought index map. So these four have been blended together into one index. Now, this is again shown as you can see here, where we actually saying standardized precipitation index has got a weighting of 40% added to soil moisture plus NDVI and evapotranspiration into one map. We chose, for example, the October map of 2019. So why are we using the convergence of evidence approach? No, there is more evidence if we use a composite index to monitor drought rather than basing alone on precipitation, as some studies have done, or on vegetation health or evapotranspiration alone. So these are the various maps, for example, for the map for the month of February 2016, using different parameters. Then we've got the map E, which is a composite map. The last map, map F, is showing the administrative divisions of Zimbabwe. So having done that, there is a process of validating the CDI that is actually important. As I indicated earlier on, there are various ways in which you can validate the CDI. In our case, we use the three methods. The first one is expert judgment, which involved stakeholders in the agricultural sector. These were taken from the 8 farming provinces of Zimbabwe, different corners of Zimbabwe, who had some knowledge about the events that were happening in the past. For this to be successful, you needed to choose one of the most recent droughts in order to do away with memory decay. And in our case, we chose 2015, 2016, as well as 2018, 2019 season in order to validate. So that's the first one, expert judgment. The second method of validating this CDI involved using observed rainfall data from weather stations. Again, we chose 8 weather stations dotted across the 8 farming provinces of Zimbabwe. As you can see, the map there is showing the various weather stations from which we obtained the rainfall data. These 8 stations represented the 8 farming provinces and do well again to represent the ecological regions, agroecological regions of Zimbabwe. Then lastly, we used the crop yield. This crop yield was obtained from the Ministry of Agriculture and again came from the 8 farming provinces of the country. Having done that, this is the results of our stakeholder expert judgment, stakeholder validation. The table is simply showing the error matrix for a specific season, 2015-2016 season, the error of commission as well as the error of omission. Then we did, again, these are the results of the observed rainfall and crop yields analysis. What we observed was that seasons with the higher yields had the least number of drought events, while those with rainfall deficits had a greater number of droughts. And there were at least two drought conditions noted in every season. And the mid-season dry spells coincided with the critical growth of stages of the maize. Maize was the crop that we actually chose because maize is the staple food of Zimbabwe, and it is again sensitive to rainfall deficits. So these are the analyses just to show you what we did for every districts, 80 districts that we worked with, coming from the 8 farming provinces of Zimbabwe. We actually show integration analysis using rainfall data as from the 2008 to 2020, and that the scatter plot again showing the case for Zvimba district, one of the districts in Zimbabwe. This is for another district, which is Masvingo district in Zimbabwe. We did, as I said earlier on, for all the 8 districts that we worked on. So what are the takeaways from what we've been doing? We noticed that the monthly accuracy of the CDI ranged from 95.6 to 100%, while the seasonal accuracy ranged from 97.6 to 100%. Seasons with the higher yields had the least number of drought events, while seasons with the rainfall deficits had greater number of the droughts. What are the final thoughts about the CDI? As we noticed, drought is modeled as it evolves from the start of the season until it ends. And the CDI is in a position to accurately depict the geographical extent, the severity, as well as the duration of the drought. The coverage of the CDI is both national and subnational. Now, seeing a global shift towards the development of remotely sensed, modeled, or composite indices being integrated into drought early warning systems and or standalone decision support tools, application and services help bridge the gap between monitoring or early warning, prediction, and preparedness through proactive drought monitoring measures. So, having developed that tool, we then said, well, to the ordinary person who is not technically minded, what is most interesting is to come up with a drought monitor map. So we developed a web-based drought monitoring platform. This is the platform, which helps stakeholders to visualize the drought conditions in a particular area over particular months and the like. The platform, however, it is actually updated on a monthly basis. In the map, as you can see, it includes the drought conditions at the grid pixel level of 5 by 5 kilometers. And the drought conditions are at the district level, which is the smallest administrative unit through which policies are designed and implemented. This is about the drought monitoring tool that we have been developing in order to monitor drought in Zimbabwe. Now, we then recommended it to the government of Zimbabwe for consideration for use in order to monitor drought. Thank you very much for your attention.
Thank you very much, Emmanuel. And it was a great presentation, and also you finished it quite on time. Thank you so much. Let's see if anybody has any question for you. No question?
I have one quick question. So is this model very Zimbabwe specific? Could it be like applied with maybe some modifications to alternative contexts as well?
Yeah, sure. It can be applied to different contexts. In fact, many countries are actually applying it. Within Southern Africa, we have got Eswatini, we also have Botswana. These are the countries. So what it differs is are the parameters, how many parameters, depending on the quality of data that is actually available in order to put into use. So it is a model that can be applied. One thing that I forgot to mention is that we did this with the support of the World Bank, financial support from the World Bank. After having realized that drought is a major problem in many countries in Southern Africa and also outside Africa. So it can be applied. Thank you.
Exactly. No, I think this is a very timely topic, especially as climate change is ravaging, different regions and continents, and the impacts are likely to become even more severe. Thank you.
So I had a quick question. So I think the study does a really nice job of developing this new metric for understanding what the drought conditions are based on a couple of different variables that you're collecting. My question is, how can this be used proactively? So it's informing what the conditions are. To what extent can that then inform on a time basis actions? So you had talked about it as a decision support tool. What sorts of proactive actions will this be supporting?
Thank you. To our understanding, this can be used as both a drought monitoring and early warning too, especially to countries that depend on rain-fed farming system. As we model the drought from the start of the season, we modeled it as it is evolving until the end of the season. This will give it will give us the opportunity time to take action, to know that now that we are for example, we are in the month of suppose a season has got 3 growing months for crops. We can actually say in the second month, given these drought conditions, then there is no hope that in the last month or so, then our crops will do well. Therefore, some proactive actions can actually be taken. One thing that is interesting is the early warning and early action that is being promoted by some development agencies. They've been actually approaching us to say, well, if we are able to monitor it on monthly basis or even on weekly basis, then we'll be in a position to say and to take the remedial measures in time, especially by providing assistance to the likely affected populations well in time before the drought hits. That's anticipatory action.
Great, thank you.
Well, once again, thank you very much, Emmanuel.